Hello, everyone, and welcome to IBM Quantum Presents the Intro to Qiskit and the Qiskit Tips and Tricks workshops. IBM is a comprehensive open source software development company, and Qiskit is used for working with quantum computers at the levels of circuits, pulses, and algorithms. Qiskit also provides tools for creating and manipulating quantum algorithms and enables running them on simulators as well as real hardware. As usual, during today's workshops, please post any questions you have in the Twitch chat, and we will stop periodically to answer them.
It is my great pleasure to introduce Abby Mitchell as today's presenter. Abby joined IBM in 2019 as a full-stack web developer before moving to the quantum computing department as a developer advocate in March 2021. She is currently working on Qiskit, IBM's open source software for quantum computers. As a primarily self-taught developer and quantum enthusiast, she is passionate about encouraging people from any background to pursue their interest in technology. Without further ado, please join me in welcoming Abby.
Hi, everyone. Should I just go ahead and get started? Awesome. I'm just going to go ahead and share my screen. Give me a shout if anything is not showing as it should do. But yeah, I'm just going to dive right in. What we're going to go through today is an introduction to quantum coding with Qiskit. We have about 2 hours for this full workshop. I'm going to go through quite a lot of content. So if you do have questions, just pop them in the Twitch chat, and then my lovely helpers from Yale and Stanford will be monitoring that, and they'll just jump in as we go through with questions as we go along, and we'll take it from there. I'm just going to be kind of going through this Jupyter notebook, but I do have it also published in my GitHub, and I think I've sent the links, and that should be coming through to you in the chat at some point as well. So if you want to go and find that notebook for yourself, download it, run it locally, then you can do that as well. Really, I think the main goal of this talk is don't worry too much about trying to, understand every single detail of the code and making your code run flawlessly. I think the more important thing is to kind of just to watch and absorb the main concepts, and then you can go maybe in a bit more of a deep dive into the finer details in your own time as well. And I'm going to post some extra resources too. So starting off, I just have this first cell here. We're just going to import some of the important modules that we're going to need to go through the rest of this notebook. We just have a LaTeX kind of visualization module here, which is just for the purpose of the notebook to show the different equations nicely formatted. So that's not a Qiskit specific thing. But then this second line here, we're going to be importing a quantum circuit, a quantum register, a classical register, which are kind of like the building blocks of our quantum circuits, which we'll get into in a bit later. Also an air simulator, as well as some functions like transpile and execute. We're also importing all the gates in the Qiskit circuit library so that we can add some gates to the circuits that we're going to build. Just a handy random circuit generator, and a couple of visualization modules as well, so that we can plot some results that we're going to see going forward. So in terms of the main contents of this workshop, we're going to go very quickly over some quantum computing basics. I am pretty much assuming that most of you are generally familiar with these concepts, so I'm not going to spend too much time on it. And there's plenty of really good resources out there for you to brush up on your knowledge as well. Then we're going to go into an introduction of quantum gates and quantum circuits and show you how to implement them in Qiskit. And then we're going to run our first quantum circuit. We're going to prepare a very simple state called the Bell state. And then that will kind of cover the most of the kind of like foundational content. And then we'll move on to thinking about how do we actually solve problems with quantum computers. And we're specifically going to take a look at the Deutsch-Jozsa algorithm in more detail. And then at the end, depending on how we're doing for time or how many questions you folks have, we'll try run it on some real hardware as well. Okay, so just getting started with a quick recap on quantum computing basics. As I'm sure a lot of you know already, classical computers run on classical bits, which are basically a series of electrical impulses, switches that you turn on and off. They run on a binary system of zeros and ones. Qubits differ from this in that instead of dealing with switches that you're turning on and off, you're instead dealing with, depending on how you've constructed your hardware, but we're essentially dealing with subatomic particles. We're looking at things on a subatomic level where the physics just works differently from classical physics, and we've entered this realm of quantum physics. Qubits will start in a state of 0 or 1, just like classical bits. But one of the key important properties of quantum computers is that we can put qubits into a state of superposition. What this means mathematically is that our qubit can be in a state that is not just purely 0 or purely 1, but we could actually get it to be a state where it's a linear combination of both zeros and ones. Once our qubit is in that superposition state, then we can do manipulations and rotations on those qubits to kind of influence the outcome that we'll get at the end of the computation. Another important feature of quantum computers is this idea of measurement. When a qubit is in its superposition state, in order to actually get any of the useful information back out that we can use, we have to run a measurement on those qubits. And the act of measuring a qubit when it's in superposition will force that qubit to resolve itself down back into 0 or a 1. And if you just took a qubit in 0, 1, put it into a random superposition and then measured it straight away, you did that 1,000 times, you would get pretty much a 50-50 chance of getting either a 0 or a 1. Like it would be it's an entirely random process, that measurement. So you get an even split of outcomes. And it's only once we start to do operations on those qubits when they're in superposition that we can start to push those probabilities to either 0 or 1, depending on what operations that we've done. Another very important concept in quantum computing is this idea of entanglement. I just like to put this cartoon up here because I feel like it quite nicely summarizes the concept. Einstein, I think it was, called this particular concept of quantum physics spooky action at a distance. Essentially what this means is that we have, let's say, I have a qubit here that I have on Earth, and I decide to entangle it to another qubit. And I give that second qubit to my friend Alice, and I send Alice to the other end of the universe. If I make a change to my qubit that I kept here on Earth, because it's entangled to Alice's qubit will instantaneously reflect that change, no matter how far away it is. So we're talking about information transfer that works faster than the speed of light, which when it was first proposed at kind of, early 20th century, this was kind of a very crazy concept, and hence why it got the name spooky action at a distance. And we're going to be using this concept of entanglement quite a lot through the rest of this talk. So moving on to circuits. I like to normally compare this back again to classical computing. You'll see this trend kind of happening a lot as I go through this talk. I always find it useful to first look at things classically and then see how we compare it to the quantum format. The way that classical computers work, you may or may not know this, in order to create your whatever algorithm it is you're running on your classical computer, at the end of the day, when you distill it down to, you're doing operations on bits, and you will build up and you do operations using logic gates. And one way of representing these logic gates is with a circuit diagram kind of like this, where each kind of line or wire here kind of represents one bit, and each block kind of represents certain logic gates that you are running on a single bit or multiple bits. And this kind of format also translates very well into the realm of quantum computing. We can use a similar kind of visualization to show how we can do operations on qubits. So again, we have a similar structure here where you have each line representing a single qubit, and then these kind of box things representing logic gates or operations that we are doing on those qubits themselves. There are a few differences as well that we will go into. For example, you'll often see any classical bits that we use for storing measurement outcomes. You'll see them displayed as like a double line like this. Sometimes they'll be, at the bottom of the diagram. Sometimes you'll see them at the end here. And then you usually have some kind of gate like this to represent doing a measurement on that qubit. So you can see here you have a single line going in, and then you're doing a measurement on that qubit, and then you're recording the output on a classical bit here. Or it sometimes looks like this, depending on how you lay out your circuit. Yes, so once we have, so how do we actually build up circuits like this using Qiskit? Well, I'm just going to show you very quickly. We can just create a random circuit very easily by calling this random circuit function. I'm just going to store it in an object called rand. And the arguments that I'm going to pass to random circuit are, the first argument will be how many qubits I want in my circuit. And the second argument will be how many classical bits. And then I want to show some measurements in my circuit, so I'll just put measure equals true. And then once I have this circuit object that I've created, I can call .draw to basically just output a nice visualization like so. So yeah, as you can see, just like with one simple line of code, I can just generate a nice circuit object and I can draw it out. I've just used the argument MPL here because I wanted to make it a nice pretty diagram. If I didn't have MPL in here, it would just give me kind of like quite an ugly looking black and white drawing. So I like to do the colorful one. Yes, so as you can see here, the qubits, the different gates, I can run this as many times as I want. It's a random, basically a random generator for a circuit. So every time I run it, I'll get a different outcome. But obviously, we want to do something a bit more intentional with our circuits. So if we want to actually build our own circuit from scratch, we can call this quantum circuit object. Here, I've just added a single qubit in here. And again, I'm just going to draw it. And that just gives me this very basic output. And we'll show in a minute how you can start building up and add all the gates that you kind of see here. If you want to add a classical bit as well onto your quantum circuit object, you just have to add a second argument, like so. And again, you can see here, we have this double line representing the classical bit here. So that's one way of building your circuit directly with the quantum circuit class, but you could also separate that out into first creating a quantum register and a classical register separately, and then combining those into a quantum circuit object. So the way that you would do that is just call the quantum register class with the number of qubits that you want. You can also give, for this object, you can give it a name if you want to, which can be quite helpful when you start dealing with lots of different groups of qubits. Sometimes it's nicer to keep track if you give it a custom name. And you can do the same with a classical register as well, just with the first argument being the number of classical bits that you want. And again, you can give a name if you want. And then once you want to combine these into your quantum circuit object, you just call quantum circuit class, the same as we did previously. And this time, instead of putting just a number for how many qubits and classical bits you want, you would pass the classical register, and then the quantum register, and draw it in exactly the same way. And as you can see, I've got 2 qubits now, 2 classical bits. Sometimes you'll see the classical bits kind of like separated, or sometimes you'll just see them together, and then the little small number here that kind of indicates how many there are. And there are different, you can do different edits to visualize it how you like. And yeah, so as you can see, this is just to build kind of the basic building blocks of your circuit using Qiskit. It doesn't look very exciting yet. It's just a couple of empty qubit and classical bit wires. And in order to start doing more interesting things with it, we need to start understanding what quantum gates are. I'm going to show you 3 different ways to represent quantum gates, which all kind of are, they're all the same thing. First is going to be the circuit box model, which is basically when you draw it out like this, you have boxes on wires. That's what I mean by the circuit box model. I'm also going to go through a bit of Dirac notation. If you're familiar with linear algebra, this should be quite familiar to you. And then we'll also see a little bit of how we represent these in matrices. It's definitely useful to have some background in matrix mathematics and linear algebra. They all kind of, it helps to, it is another tool in your toolbox to help you kind of navigate this space. Me coming from a more of a software background, this was something that I had to put in some effort to learn again, separately, coming from the software side. But yes, you will see, we'll only be going through things at quite basic level for the purposes of this talk. So I recommend going and looking at it more in depth in your own time to really feel confident with the concepts. Okay, so let's just start very simply with, I'm just going to zoom in actually, my screen might be a bit big for you all. So let's just start with some regular bits. If we have a bit string of 0 to represent this in Dirac notation, I'm going to use this ket. This is called a ket with a straight like bar here, and then this kind of sideways hat thing and a 0 inside. This represents a qubit that is in the 0 state. If we were going to write this exact same format in a matrix, we would just get a column vector like this with a 1 at the 0th index and a 0 at the first index. Similarly, for a bit string of 1, if we were writing this in Dirac notation for a qubit that starts in a state of 1, we would again write this ket notation with a 1 in the middle. And the matrix for this would be a 0 at the 0th index and a 1 at the first index. That's like the very super basic way to start off with this kind of notation. Make sure that you are comfortable and you remember this. You're going to need it a million times with your journey into quantum computing. Next up, we're going to talk about the X gate. So this has a classical equivalent known as the NOT gate, which basically all the NOT gate does in classical computing, the same as in quantum computing, is it will do a bit flip. What this means is it will take a bit that's starts at 0, you apply a NOT gate to it and it will flip it to a 1. Or if you start with a 1 and you apply the NOT gate, you will flip it to a 0. And the same with qubits. If you start with a qubit in the state 0, you do an X gate, you'll flip it to a 1. And if you start with a qubit in a 1, you do an X gate, you'll end up with a 0. It's very simple. And to implement it in Qiskit is also really simple. So let's say I have this, I just have this quantum circuit object that I've just initialized with a single qubit. In order to then apply a NOT gate or an X gate to that quantum circuit, all I have to do is call .x and then pass the index of the qubit that I want to apply that X gate to. So like so. If I had multiple qubits, if I had like quantum circuit with 2 here, I would need to make sure that I was applying it to the correct index that I want that X gate to be applied to. So say I wanted to apply it on the second qubit, not the first qubit, I would put the index of 1 here, and then I would get something a bit like this. So again, very simple. We can also with Qiskit get a bit more information about what that X gate is itself in terms of its matrix layout. Every gate has its own class. So an X gate is a capital X gate. And we can just call this gate to matrix function to kind of retrieve what the matrix format of that is. So this is really useful function if you have more complex gates specifically, and you want to check what the matrix format is, you can do that with this to matrix function. And I'm just calling array to latex here just for the visualization purposes in the notebook itself. So this is what the matrix looks like for an X gate, which I'm showing to you because it's a nice kind of way to see how the matrices work when you when we can see how we can apply that matrix to our 0 state or our 1 state. So we're going back to Dirac notation. If we have to represent an X gate being applied to a qubit in state 0, we would take this this ket, this 0 ket, and then just write a capital X in front of it. And as we said earlier, applying an X gate on a qubit in the 0 state will flip it to the 1 state. So if we wanted to expand this out into matrices, we can see that if we have this 2 by 2 X gate matrix, apply that to our 0-bit string. We do the maths. You can see that it works by turning it into the 1-bit. Again, conversely, if we're applying it to a qubit in the 1 state, exactly the same. Capital X, and then the 1 will flip it to a 0. And again, with the matrix multiplication, you can see that that it works mathematically as well. So really the main concept here is to understand that when you're applying a gate to a quantum state, essentially what you're doing is a matrix multiplication. And the larger the multiplication that you're doing, the more difficult it becomes to compute classically, and you start to see why we need quantum computers to handle such big calculations. The next gate I'm going to go into is the Hadamard gate. So this gate doesn't have a classical equivalent. It is the gate that will put our qubits into a superposition. Obviously, classical bits don't have superposition, so hence you don't have a classical equivalent for it. So if we wanted to show what that looked like in Qiskit, again, we can have a look at what the matrix looks like by calling this H-gate class and just calling the to matrix function. So for the H-gate, what you have is, again, a 2 by 2 matrix with 1/√2 in every space except for the bottom right one, which is a negative. You can also take the 1/√2 out and just have it be 1, 1, 1 minus 1. It's just another way of writing it, whatever you find the easiest. And if we want to use Qiskit to apply this Hadamard gate to a quantum circuit, we can do it in a very similar way that we did with the X gate. We have a quantum circuit object here with 1 qubit. And again, we just call .h and then the index of the qubit that we want to apply that gate to. And if we draw it out, you can see that will give us a nice visualization with that H gate. Going again back to Dirac notation and the matrices, to show an H gate being applied to a state of 0, we can write, we have our, again, we just do a capital H followed by the 0 ket. And what this outcome will give us is we write it out in shorthand as the plus state. But if we wrote it out longhand, it would look like this. And this is where, as I was saying earlier, when you put something in a qubit into superposition, you're getting mathematically this linear combination of zeros and ones. So we can't say it's definitely 0 or definitely 1. We have 1 over root 2 times 0 plus 1. And if we wanted to do it right out in matrix form, it would just look like this. Similarly, if we want to apply a Hadamard gate to the state 1, we would get what's called the minus state out. And this, again, if you expand it out, looks very similar, but instead of the plus here, you have a minus instead. And with matrices, it looks kind of like this. And this kind of brings me on to the point that the H gate and the X gate that we've just seen are what we call unitary gates. This means that they are reversible. If you do a Hadamard followed by a Hadamard, you're basically just undoing the Hadamard that you just did. So you'll have no change. We say we get the identity matrix. And similarly, if you do an X followed by an X, you'll also get the identity. So what this means is that if you do an X applied to a 0, you'll get a 1. And then if you do an X on that 1 again, you'll get a 0. And similarly for H, if you do H applied to a 0, you'll get a plus. You do H again applied to that plus state, you'll get back the 0 state. If you apply an H to a 1 state, you'll get the minus state. And then if you apply H again to that minus state, you'll get back the 1. So these identities are going to be quite useful later on when we start going through the Deutsch-Jose algorithm. So yeah, just keep them in your mind. So next we'll move on to the controlled NOT gate. So this is the first 2-qubit gate that we're going to go through. We sometimes call it the CX gate or the C0 gate. And essentially what this is a controlled NOT gate, a controlled negation. And it works by, you're essentially doing a controlled bit flip. If you have a qubit that is a control, you have one qubit which is a control qubit, you have another qubit which is a target qubit. What this will mean is that we will only do a bit flip on that target qubit if the control qubit is in a 1 state. So if we wanted to show the matrix again with Qiskit, same as before, create this, call this CX gate class, call the toMatrix function, and you can see here it's a 2-qubit gate, so it's a 4x4 matrix this time instead of 2x2. And to draw it out in the circuit box model, what we would do is, again, here I'm just creating a quantum circuit, this time with 2 qubits, and this time I'm calling .cx on that circuit. And what I'm calling here is the first argument here is going to be which qubit I want to be the control qubit and which qubit I want to be the target qubit. Drawing it out like this, you can see that the small circle one indicates that the qubit is the control qubit, and the larger one indicates that this one's the target. So essentially what this means is that if qubit 0 is in a 1 state, then this gate means that qubit 1 will also get flipped. But if Q0 starts in the 0 state, Q1 will not get flipped. Q1 will only get flipped if Q0 is a 1. So essentially what this means is if we were to measure each of these, if Q0 is 1, then Q1 is also always going to be 1. But if Q0 is 0, then Q1 will also always be 0. And so for Dirac notation, to write this out, we can just use capital C0 followed by this Dirac notation, this ket, with this time we have 2 zeros because we're indicating that we're applying this onto 2 qubits simultaneously. Okay, so I've just shown you 3 quantum gates there, and we are going to put them all together to create your first kind of proper quantum circuit. And we're going to create a state called the Bell state. So first up, let's just create a quantum circuit with just with a single Hadamard gate on it. We're going to make it a 2-qubit quantum circuit with 2 classical bits as well. Very simple like this. If we were just going to measure this straight away, what we should see is when we get some outcomes that we'll get a 50-50 split of a measurement outcome being in a 0 or a 1. So to show this, we're going to add just a barrier. This is pretty much just for the sake of visualizing the qubits. It lines things up nicely. And then we're going to add these measurement gates here. So to add the measurement gates, you call .measure. And then I'm passing it 2 lists of this first list is which qubits I want to apply measurement gates to. And this second list is which classical bits I want to record that data to. So I put a measurement gate on the first qubit, it will record the outcome on the first classical bit. And then I add one to the second qubit and it will record the outcome on the second classical bit. So we've created this circuit, but we haven't actually run it on any hardware or anything right now to actually get any outcomes from it. And we can't get any, I mean, this is quite a trivial example. So I've told you what the outcome should be, but, you know, hypothetically, when you're building up these much bigger computations, like you won't know what the answer is. So you'll want to run it on a simulator or on real hardware to be able to get those results out. So we're going to just run this one very quickly on a simulator. So we're just going to first fetch that simulator that we want to use. We're going to use the air simulator by calling air.getBackend. Air is the simulator module for Qiskit. Then what we're going to do is we're going to call the transpile function, and then we're going to pass our circuit onto and our simulator. Transpilation basically is the process of taking that circuit object that we've created and kind of adjusting it to put it into a kind of more optimal structure to run on whatever specified backend that you have. We're not going to go too much into that today, but just know that once you create your circuit, there is some stuff that happens behind the scenes to adjust it slightly to make it compatible with whatever hardware it is that you're running and make it and optimize it as much as possible. So then we call our simulator to actually run the circuit on our simulator. We call sim.run. We pass our transpiled circuit, and then we have to specify the number of shots. The number of shots is basically how many times we want the circuit to run. As I said, because we're dealing with, you know, random processes with qubits in superposition, we need to run the experiment multiple times to be able to see the probability distribution of the outcome. And we call .result just to kind of get the result back and store it. And counts, used by doing get counts, it will kind of count up for us how many times we got a result of 1 versus a result of 0. So if we run that, we can see here, we have 2 qubits. We put an H gate on one of them. So this means that we haven't done anything to this second qubit. So this one's always going to be in a 0. So that's why you have a 0 option in all of these. But then you have 50% of the time, roughly, you have a one getting recorded here, and 50% of the time a 0, which is in line with what I told you earlier, right? If you take one qubit, you put it into a superposition, and then you measure it, 50% of the time it will be a 0, 50% of the time will be a 1. And so we can see that pretty clearly here. We can also call a plot histogram visualization module to kind of get like a nice pretty graph of that kind of outcome. And there you can see how it puts the output. So we can adapt this circuit that we created just very slightly to create what we call the Bell state. The Bell state is really the simplest implementation of entanglement. And all we're going to do is we're going to add a CNOT gate after that first Hadamard. So I'm just going to create a Bell state. I'm just going to call it Bell. I'm going to create a quantum circuit, again, with 2 qubits and 2 classical bits, adding an H to the first qubit as usual. And then what we're going to do is add this CX gate, controlling on that first qubit and targeting the second qubit, and measure it. So we get something that looks a bit like this. Just a quick for the sake of completeness, to write it out, if you were going to write this out in Dirac notation, you would write it out like this. We're applying a C0 to qubits where one qubit is in a state of 0, that's this qubit 1 here, and another qubit is in a state of plus, because we've added that. Remember, when we add a Hadamard to a qubit in a state 0, we get the plus state. Just bear in mind that with Qiskit, we reverse the order of the qubits. So Q0 here is actually going to be the very last qubit that's in this notation, and this qubit 1 is this one on the left here. That can throw people off a lot, especially at the start. So just bear that in mind when you're working with Qiskit. And so then when we expand it out mathematically, what we'll see is we're going to get a superposition of 0, 0, and 1, 1. If we were just going to do like we saw earlier, instead of getting 0, 0 and 0, 1, we're going to see that because we've added this C0, we're going to get 0, 0 and 1, 1, because now we are entangling these two qubits together. And we can run this in exactly the same way on our simulated backend with 1,000 shots. And as we can see, as we predicted, we'll get pretty much an equal split of 0, 0 and 1, 1, because we have this C0 here that is checking when, if say after the Hadamard gate has appeared, if it's been a 1, then this C0 will flip this second bit. So we'll also be measuring a 1 here, where previously we would only measure a 0 for this qubit. And again, we can print it out in a histogram and see a nice visualization of that 50-50 split. So this is really the simplest example of using Qiskit with quantum circuits and simulators to kind of demonstrate entanglement. And yeah, this is kind of really like the bread and butter of so many quantum processes and quantum algorithms. So next we're going to talk a bit about, actually maybe now might be a good time to pause for if we have any questions. I don't know if anyone's asked anything in the chat.
Hey, Abby, we don't have any questions in the chat, but I actually have one.
Sure.
So I was wondering if there's a difference between creating a classical register manually or when using the second argument of quantum circuit, if there is a difference.
Yeah, for sure. So I'm trying to think of, I don't have like a good example of showing it to you off the top of my head, but there's definitely like certain situations where, for example, if you have multiple different kind of sets of qubits and you want to maybe name them slightly differently or use them for different functions, at certain point it becomes more difficult to just create a full quantum circuit straight away. So yeah, I can't think of like a specific example that's nice to show you right now, but you definitely you have like slightly more freedom when you're just creating the registers themselves. You can the way that you can like build up quantum circuits is you can kind of like stick different registers together. So maybe if you had like 3 different quantum registers and 2 different classical registers and you wanted to use some and not all of them, it just kind of becomes a little bit easier to manipulate those qubits. But mostly for the purposes of this, like just using the quantum circuit object is fine. It was mostly just a kind of development choice to make it easier for software developers, if I understand correctly.
Thanks so much. There's another question. How do we create gates like the Hadamard gate on actual quantum hardware?
That is an excellent question for someone that actually works in hardware. I'm from a software background, so how we actually implement these things in hardware is a bit complex, but essentially our gates are kind of microwave pulses that you can calibrate. And there is actually a whole pulse module in Qiskit that will let you kind of like create a Hadamard gate from microwave pulses themselves. But that's not really my area of expertise, so I can't say much more of it than that. But definitely go and check out the Pulse module in Qiskit, because that will let you kind of create your own custom gates down at like the pulse level, for those that are more interested in how things work closer to the hardware.
And then if you don't mind, I also have a question. So if I wanted to do like I guess like a transverse gate, like a Hadamard's along an entire register. So if I had a quantum circuit, could I choose whether to address it to a range of qubits in the circuit or to a register? Do I have to use the register name if I've created the circuit using registers?
Oh, okay, I see what you're saying. No, so.
Or maybe you could also, if you like would feel comfortable explaining maybe a little bit more about the Python internals of what these two objects actually are.
I would, but I'm not sure I'll have time to go into them and get through the rest of the module.
No worries.
I can always point you towards the documentation. But yeah, if you do want to like add, Hadamard gates, for example, to multiple qubits at once, easiest thing to do is kind of like you can create a for loop that goes through every qubit in the quantum circuit. Or yes, if you have that, that is one of the easier places where if you have a quantum register, you can use like splicing. So you can specify, okay, I only want to apply Hadamard gates on like between qubit 0 until the end of the register or not. So yeah, that is a good example of where you can have like slightly a bit more control, especially if you're more if you're more familiar with Python and stuff and you want to do that kind of level of complexity, then you can. Yes, but again, like don't have the time to go into it in like a lot of depth right now.
Sorry, yeah, thanks.
No worries. I think there might be some examples later on in the code where I did do that. I will remember to call them out when I come through them. Okay. I guess we'll pause there for questions and move swiftly on, and I will pause again at the end of the other section. So now I want to really talk about how we solve problems with quantum computers. If we have a universal quantum computation, we can implement any classical computation. But the point really is that not every algorithm can be implemented on a quantum computer efficiently. By that, what I mean is, we don't need to do everything on a quantum computer. You're never going to have a quantum computer in your laptop or on your phone, because classical computers can do everything you need perfectly well. The overhead of trying to use real quantum hardware to do like quite trivial things that classical computers can do well enough is not very, there's not much point to it. I think sometimes people tend to think of quantum computers as kind of competing with classical computers, and that one day quantum computers will replace all classical classical computers, but that's not true, at least not in our lifetime, but I don't think. I think we're probably going to see more of quantum computers being used in parallel with classical computers in order to make things that classical computers find very difficult easier. So there are a few examples of specific areas that a quantum computer can do kind of faster or more efficiently. One area in particular is simulating quantum systems. I think it was maybe Richard Feynman that said the famous quote, nature isn't classical, damn it. So if we want to be able to simulate nature, it needs to be quantum, which is very true. If you go down to kind of looking at any quantum system, anything on a subatomic level, if you want to look at how molecules work, you want to simulate anything on a kind of atomic level, very, very quickly, even for the simplest of problems, classical computers become, the calculations are just too massive for classical computers to be able to do efficiently. So we have, for example, one quantum algorithm that is, that can do this kind of thing much more efficiently is the variational quantum eigensolver, which is used for simulating molecules. There's also other areas of mathematics that could benefit from a quantum speedup. One example is the fact that quantum computers are known to be able to factor numbers in polynomial time. This comes under Shor's algorithm that was published in 1994 and uses specifically an algorithm called the quantum Fourier transform. This is something that is very, very difficult to do classically, but which with hardware that is good enough, quantum computers can prove advantageous. And there's also certain optimization problems, for example, in like machine learning or options pricing, financial models, things like that, where you can get kind of quadratic speedups by using quantum computers. And one example is a quadratic speedup of searching of an unordered list, which you can do with Grover's algorithm, which was first published in 1996. So if we want to think about what I just shown you in terms of circuits and simulators, and think about how do we actually translate that to problem solving in a quantum, in a kind of a quantum computing abstraction. I like to kind of use this visualization to show how that would work. So you might have a real world problem like, I want to simulate a molecule. What you would do is then develop a quantum algorithm. You could either, in Qiskit, for example, there are certain packages that will let you just call the algorithms immediately. But what you're actually doing under the hood is kind of creating a quantum circuit. And you can also develop your own algorithm by putting together a quantum circuit itself. So you can kind of think of quantum algorithms and quantum circuits as it's kind of roughly the same thing. Once you have a quantum circuit that is doing your algorithm and your computation that you want, we have to actually compile it and transpile it down into something that can actually be run on either a simulator or on the hardware itself. And that kind of shows you the anatomy of how we solve problems with quantum computers. And so the main kind of example that I'm going to give you today is we are going to solve a classical problem in a quantum way using a quantum algorithm called the Deutsch-Jozsa algorithm. The problem that we are going to do is might be familiar for those of you that have maybe studied computer science, but it's the question of how do we figure out if a function is constant or balanced. So going back to the classical realm for a minute, there are 4 classical operations that you can run on a single bit. The first one is the identity, which means if you have an input of X, you just do nothing to it basically, and you get the same output. You can also run a negation operation, which will mean that whatever input you put in, your output will be the opposite. So if your input is a 0, your output will be a 1. If you input a 1, your output will be a 0. And then we have what's called like the constant operation. So we have a constant 0, which basically means that no matter what your input is, your output will be 0 every time. And similarly, constant 1 means that whatever your input is, your output will always be 1. And so we call these ones the constant 0 and constant 1, we call them the constant operations, and then the other ones we call balanced operations. So given we have those 4 types of operations, let's say we have a black box and we have an input X and an output Y. How do we figure out what's in the box? So for example, if we just ran the function once, we had an input of 0 and we got an output of 1. That means we could automatically tell, okay, it's either going to be a negation function or it's going to be a constant 1 function, because our output is, we put in a 0 and our output was 1. But how do we figure out which one it is out of negation or constant 1? How do we tell if the box is constant or balanced? So for classical computations, you would need to run f of x at least twice in the best case to be able to figure out whether that box was constant or balanced. If you're, if you're into the big O notation and you want to know that, in big O notation, that means that it would have O of n over 2 plus 1. So what I'm going to show you is how we can build a algorithm with Qiskit that with an algorithm called the Deutsch-Jones algorithm, which will let us only need to run f of x once to know if it's constant or balanced, meaning we'll have an O of 1. So this is was an algorithm that was published back in 1992 already, and it's quite influential because it was really the first example theoretically of a quantum algorithm that we know for sure performs better than a classical algorithm. Because pretty much up until then, you know, quantum computers, you couldn't really make a case for why we should be investing in quantum so much if like it's not even going to give us an advantage over classical. And this paper was really you know, quite groundbreaking in showing that, like, yes, there are things that quantum computers can do better than classical computers. Theoretically, if you have good enough hardware, which is probably the main blocker at the moment in reality. Okay, so we've got our problem, we know which algorithm we're going to use. How do we implement this in quantum circuits? So first things first, what we're going to do is we're going to prepare our oracles, our black boxes. We're going to prepare 4 of them so that we can kind of test them out and see how they work and go from there. But before we do that, we need to translate this black box problem into a more kind of qubit situation. So to do that, we're actually going to be using 2 qubits. And we're going to have our input qubit is going to be on, we're going to have 1 qubit for an input and another qubit that starts in the state of 0, but then after we apply the black box is going to store the output. So we'll have the input will always be on Q0 and that will be stored on Q0, and then the output will be stored on Q1. And we're going to create 4 oracles. The first one will be identity, the second one will be negation, the third one will be constant 0, and the fourth one will be constant 1. So the first oracle we're going to put together is going to be the identity. So remember what we said with the identity was whatever our input is, our output will always be the same. But now because we're using 2 qubits, we need a way of basically transferring like that output onto that second qubit. So the way that we'll do this is just by adding a CNOT gate, so that if the input is 0, nothing will happen and the output will stay as 0. But if the input is a 1, then this second qubit will get flipped and the output qubit will be a 1 as well. So to apply this in Qiskit, I'm going to be using the quantum registers. The reason that I'm using them as registers here is because I can name each of the registers. So for visualization purposes and manipulating them a bit later, it's easier. So this is one to answer the question from earlier. This is one kind of example of why it can be more convenient to use the registers instead of just the quantum circuit. So I'm creating a quantum register called input that I'm going to actually, you know, verbosely name input, and a quantum register called output. Each just has 1 qubit in it. Then I'm going to create this quantum circuit and name the whole circuit itself the oracle. I'm going to apply that CX gate with the input being the control qubit, the output being the target. And then what I'm going to do is I'm going to take this whole quantum circuit I've created and call toInstruction. Basically what this does is it just stores it as an instruction object, which means that we can basically use it later when we add it onto other circuits. I'm just drawing it out here. I can see that, and you can see here now why I've opted to go for the separate registers, because now I have a nicely named quantum register for the input qubit and for the output qubit. If I just did it as a quantum circuit, I wouldn't be able to name everything so specifically. And I also set this initial state equals true in the drawer itself, just so that I can, just because I find it quite helpful to see what state my starting state is for those qubits. By default, all qubits start in a 0 state, but sometimes you might want to start in a different state. But yeah, so I find it helpful to just explicitly print it out. Next up, we have the negation oracle. So to do that, we're going to create a circuit that's pretty much exactly the same as the identity one, but all we're going to do is add an extra X gate here on this output qubit. So this time, if our input qubit is a 0, our output, our C0 will not flip the second qubit, but then this X gate will. So that will mean that our input stays at 0, our output goes to 1. Conversely, if our input qubit is a 1, then this C0 will flip this bit to a 1, and then that X will flip it back, so the output will be 0. And so to create this, I'm going to just go through exactly the same thing. And this time, I'm just going to name when I convert it to an instruction, I'm just going to call it Oracle 2. Earlier, I called it Oracle 1 for the identity. And this one is just 2, so that I'm storing it so we can use it a bit later. There we go. Yeah, pretty simple change. Just adding that one extra X gate here on that output qubit. And again, like, as you can see here, when you're calling these gates, it is sometimes easier to mention things by the register themselves rather than the whole quantum circuit. And what I can do is, like, for example, if output qubits had multiple qubits, I could say, okay, I only want to apply it onto like the second qubit in my list of output qubits. So that's, again, how you can use what I was saying earlier. Like, for example, let's say I had, I don't know, for the sake of argument, let's say I had 10 output qubits. I could say, okay, I only want to apply this X gate on like the first qubit of the output qubit, which would make it look like, you see, like this. I have that level of control now because I've split it out into quantum registers. Or I could say, I want to go from like the first qubit, output qubit 1 to like the end of like all of them. So everything except the first output qubit wants to have an X gate applied. I can do it like that. As you can see, it kind of prints it out like this. Yeah, so this is kind of what I was saying, some examples of how you can, if you split things out into registers, then you can use a few more Python tricks to just, you know, apply your gates a bit more flexibly. I'm going to put this back now because this is not a good oracle to use later on. What were they doing here? And we just want this on the output qubit. Okay, great. Back to the oracle we need. Yeah, so this is now saved as an instruction in Oracle 2 that we're going to call a bit later. So next we have the easiest of the oracles to put together, and that's constant 0. So this basically, this oracle, remember, no matter what the input is, the output is always 0. So because our qubits by default start in the state of 0, this output qubit will always be 0. So we're just going to have we're just going to create an empty box basically for this one. So for this, to create this oracle in Qiskit, just exactly the same way, I'm just going to create this quantum circuit, but instead of adding any gates, I'm just going to go straight ahead and save it as an instruction. Yeah, and that's essentially all the gate will look like internally. It's just empty. The final oracle that we're creating here is the constant 1 gate, which is very simple, just adding an X gate onto that second qubit so that when whatever the input qubit is, the output qubit always gets flipped and always ends up being a 1. And you kind of know the drill by now. Quantum register for input, quantum register for output, put it together into a quantum circuit. We're going to add an X onto that circuit just on the output qubit, save it to an instruction. And yeah, as you can see, we have it there. So putting all of those oracles just together, this is what, you know, obviously because we're constructing this problem ourselves, we know what our black boxes are and what our options are. But you can imagine theoretically someone else has prepared these oracles. So when we see later on, like you could write a for loop to just choose a random one of these 4 and stick them in. But we know what they are just because we're going through this as a learning opportunity. So now we're just going to add our oracles onto just a random quantum circuit that we have. just to test out that they are working how we expect them to. So I'm going to create a classical register to store the results. I've got a quantum circuit that I'm going to have with input registers, output registers, and that result classical register. I'm just going to create a couple of barriers just to keep things nicely laid out visually. And then I'm going to call this .compose function, which is basically going to take any of the oracles that I previously stored as an instruction and essentially add it to the circuit that I've just initialized here. And then I'm going to measure it. So if we print it out, it would just look like this. So I've created this quantum circuit object. I've added my oracle onto here, and I'm just measuring. I can like switch it up, do anything. If I wanted to add the second oracle on there, I could. But yeah, so, but as I've given them all that oracle name earlier on, like we can't see just by like looking at it visually which oracle it actually is until we start running it. So if we were going to run this on a simulator just to check that it works, we would expect, okay, if we've added our oracle 2, that means that we've added a negation. So when we do a measurement, we should see that our output qubit, we should often get a 1 state out. Or a 0 state. Why did that? Oh, because I didn't rerun this again. No. Save this correctly. Oh no. Pose oracle 3. That is strange. Let me see what I've done here now. Created this oracle. Run all these oracle codes from the start just to check that I did that. Output. Ah, okay. I see what I did. So this should actually be but to instruction. I didn't save them correctly in the onto instruction. Okay, so now if I run oracle 1, we should see that the output that I get should be a 0, which is correct, what I want. If I run oracle 2, I should see that the outputs that I get is a 1. Yes, now we got it. If I run oracle 3, we should see also getting an output of 0. Yep. And then oracle 4, running it, I should get an output of 1. Yes, okay, great. Now we're heading in the right direction. Yeah, so yeah, bear in mind, if you pulled the notebook, there might have been a typo for one of those oracles. So yeah, this is why always good to check your oracles when we're setting them up before we actually start using them. So now we have our 4 oracles correctly constructed and saved in the correct namespaces. Now we can start actually putting together this Deutsch-Jose algorithm, and we'll show how we can start measuring. When we were measuring things now, we'll be able to check if something is constant or balanced. Okay, so I'm just going to run this quickly so we can see it visually. visually, this is what the most basic Deutsch-Jozef circuit with 2 qubits looks like. We have our oracle, and then on our kind of just before that oracle, all we have is an extra X gate here. We have 2 Hadamard gates on each, and then finally we have a Hadamard gate on that first qubit. And this time, what we're going to do to check, we've just checked through measurements that when we measure the output qubit, we get the outputs we expect from each oracle. So to be able to check now if something is constant or balanced, we're going to run a measurement on this first qubit here. And I'm going to show you how that works in a bit. So just to create this, all I've done is, again, created a quantum register, a classical register, given it the names that I want to have. Added an X gate on quantum register at the first index, and then to add a H gate on everything in that quantum register, I can just give the full register. I don't have to specify anything specifically. Then here, what I've done is I've called the dot append function, which is basically saying, okay, I have this circuit. It's a bit similar to compose, and so I'm just using this to append oracle, and I'm specifying which qubits I want to append that oracle to. So I'm appending it to the first qubit in the quantum register and the second qubit in the quantum register. And then adding that final H gate, and then measuring, just doing the one measurement here. Okay, so the way that I've constructed this, this circuit now, when I execute this on a backend, this function, by the way, this execute function is basically a shorthand for what we saw earlier with the transpile and run. Mostly speaking, you should use transpile and run. That's like the best practice way to do it. For me, I'm just being a bit lazy here and doing it in one line by using execute, but it's maybe the less maintained of the functions. Again, just passing the circuit, and the backend is a simulator that I initialized earlier. I'm just going to show now that with one shot, if I get the results and the counts, I'll be able to see if this oracle is constant or balanced. And I'm just doing a bit of Python kind of tidying up here to print it out nicely. But basically, if this qubit 0 is a 1, that means that the oracle is balanced. And if that qubit 0 is a 0, it means that the oracle is constant. So we can see here, because I've added, which oracle did I add? I added oracle 1, which was, let me remember correctly, which is the identity oracle. And remember, this oracle is a balanced oracle. I'll be able to see now when I run this algorithm, it's balanced. And yes, you can see, voila, it's balanced. So what have I done here? Why just by adding a couple of extra gates and a few bit of superposition have I suddenly managed to tell in a single shot that the oracle itself is balanced or constant? So if we take a look at these 4 oracles that we have, really what we are looking for is the difference. What is the difference between these balanced oracles and these constant oracles? And I mean, it's a pretty simple spot the difference exercise. The balanced oracles have a C0, whereas the constant oracles do not have a C0. So really what we are doing is we are, with the Deutsch-Jozef algorithm, is just detecting for the presence of that C0 in our oracle. And how are we doing this? If our oracle box is closed, like we can't see what's happening, how is that input qubit now kind of adjusting itself and tracking that change? This is because of a trick called phase kickback. And if you can understand the concept of phase kickback, this will be really helpful for you for quite a few other algorithms. So we're going to go through that, that concept right now. How are we doing for time? Okay, we're doing good. Okay, so let's just print out our circuit again, just so we have it here to look at. First of all, what we're going to do is we're just going to have a look at this first chunk here. So let's say we have, so we're just going to build out our X and our two H's. So looking at this in the circuit box model doesn't really tell us very much about why this is what's really happening here. So we're going to go back to the algebra and really kind of understand mathematically what is happening. So remember we saw earlier how if you apply a Hadamard gate onto a 0 state, you get a plus state. That is what is essentially we're doing here in this qubit. And then we also said that if we apply a Hadamard gate on a 1 gate, what we're doing is we're getting a minus state. And that's what we're doing on Q1 here. We've put it into the 1 state by adding this X, and then we're applying that Hadamard. So mathematically, qubit 0 is in this plus state, and qubit 1 is in this negative state before it goes into the oracle. If we want to again expand it out mathematically, we have a state at this point. We have a state of minus and plus. I'm just highlighting here to remind you which ones are qubit 0 and qubit 1, as they are switched in Qiskit, as I mentioned earlier. So mathematically, if we expand this out, we'll get a state which has got 0, 0, 0, 1, and then a negative 1, 0, and a negative 1, 1. I'm not going to go through the maths in much more detail than that, but yeah, just remember that this is what it looks like mathematically. And so then remember we said that in the oracle, really what we're trying to do is detect a C0. So if there's no C0, by the time the oracle is finished doing its thing, qubit, the state will kind of still be similar to this, except for the other stuff happening. But then if there is a C0 present, imagine our oracle has now applied some C0. What we're doing here is we're applying a C0 onto this negative and plus state. So if you expand out like this, essentially what the C0 does is you're flipping the sign of these first and second and fourth term. Compare it to what it has here. If there's no C0, you have positive, positive, negative, negative, but here we have now positive, negative, negative, positive. Again, I'm not going to go into the maths. You can go and look at the research papers. You can go and brush up on your linear algebra and do the full proofs in your own time. For the purposes of understanding conceptually what is happening in the Deutsch-Jones algorithm, this is the most important piece. Just by adding that C0, we're not changing the state specifically, we're just changing the phase, we're changing the sign. So if we factor this out again, we are ending up, instead of having a minus and a plus state, by adding that C0, we're ending up with two minus states. So then if we, again, looking back at our oracle, we've done our X gate and our Hadamards, we've applied our oracle. Now we're adding this extra Hadamard again. And this is because, and this is where we should remember those circuit identities that I showed you earlier. Remember, if we apply an H on a 0, we get a plus. If we apply an H on a 1, we get a minus. So conversely, if we apply an H on a plus, we'll get a 0. If we apply an H on a minus, we'll get a 1. And that is why we can tell now if there was a C0 or not inside the oracle, because remember, if there was a C0, we end up with a negative state. And if we apply a Hadamard on that negative state, we'll end up getting a 1 measured out. To kind of show you the full flow here, let's say, for example, if a C0 is present in our oracle, we start off with our state in a 0, 0. I just want us to focus on this Q0 state for the moment. The Q1 state is maybe not so important for understanding this concept right now. So we'll just focus on this one. We start off in that 0. By the time we've applied our Hadamard here, we've converted to a plus. And then as we saw, when we apply a C0 on that minus plus state, it will convert that to a minus minus state. And then when we apply that Hadamard, we'll convert that minus state to a 1, which is why we will measure a 1 only if the oracle is balanced, because a C0 is that. And conversely, with when your oracle is constant, you don't have a C0, you don't get that change from having your input qubit be a plus to a minus. It will just stay as a plus. So then when you apply that Hadamard again, you'll get a 0 out, which is why you measure a 0 only if the oracle is constant. So yeah, there we have it. We've kind of shown how we can implement this algorithm with Qiskit. We still have a fair amount of time to do some of the physical hardware stuff. So actually, I think now might be a good time to stop for questions.
We have a few questions. The first one is about simulating non-unitary processes. So this viewer is wondering if is there any way to simulate a non-unitary process, such as like an open quantum system with decoherence using just unitary operators? And if so, is there code available on Qiskit to do so?
That is a very good question, to which I say, so non-unitary operators, I think there should be. I don't know specifically, but what you can do is if you go to qiskit.org/documentation, this will give you the full this is the full documentation site for Qiskit itself. And if you're looking for like specifics of simulators, the air simulator is not the repo that I specifically work on, but you should be able to find it here somewhere. We are redoing this documentation site, so sometimes it is difficult to remember where things have been moved to. Yeah, so if you have a look through the air documentation, you should be able to find that. I don't know off the top of my head what the specifics are that you're looking for and if it's available, but definitely go have a look through the documentation. Were there any other questions?
Do barriers exhibit a particular function in Qiskit?
No, the barriers for this are like purely just because if I was going to what do I have not one here? Actually, I didn't even really need to add barriers there. I don't know why I did. I mostly just use them because visually, like it sometimes helps to spread stuff out a bit. Like sometimes, like I have a nice layout here. Actually, I didn't need barriers here, but I basically use barriers so that you don't get like your gates kind of like squished up in a way visually that you don't want them to. So I think, where did my example go? Right at the top. I had okay, so like here, for example, I think if I didn't have a barrier, then like the measurement gate would kind of get squished up and make it just look, oh, okay, well now Jupyter Notebook has been storing everything, so start again. Yeah, so you see here, like this measurement gate would kind of get squished up with the H. So it's purely like a visual thing. It doesn't really have such a strict actual kind of implementation. I hope that answered the question.
Yeah, great, thank you. And another question we have in the chat is, why does IBM flip Q0 and Q1 for the bell sticks?
Yeah, that's a very good question. So the short answer, okay, basically for historical reasons, because when the programming language was first developed, there was most of the kind of quantum computing theory is done by, theoretical physicists, not necessarily coders. But when you're developing the software, there was like specific reasons in the like initial development of the package, which meant that like from like a computational like code writing perspective, it made more sense to reverse the endian that way. yeah, so it's always kind of like a point of contention. Like everyone prefers it to be a different way, and like some of the more kind of like, I think, hardcore software developers like firmly believe that no, it should be the way that it is in Qiskit, and other people probably are more from like the quantum physics background think no, actually we should like match it to what is done in theory. But yeah, it's like kind of like it's an area of debate, and the decision was made historically, and it's kind of not really changeable now. That's kind of the honest answer. It's kind of just an inconsistency we have to learn to live with as users.
Very interesting. Do you have a strong stance on which what it should be?
So my opinion is that we should make it as easy as possible for like a user perspective to like it should be as intuitive as possible for a user. Mm-hmm. So I personally think maybe it should be the other way around, because it's kind of unnecessarily confusing. But I think when you kind of get down to a lot more complex problems with like computational efficiency, I have faith that there is genuine reason why it's not this way around.
Yeah, that makes sense. And one last question is there a way to visualize the qubits in the non-Qiskit order when outputting the states?
Yeah, so let me take this one, for example. Let me see if I can remember how to do this. So I think there is a function called reverse bits. Bits, which I think you call like this, which theoretically should, that didn't do anything. I would have to look through the documentation. It's not a function that I would use very often, but it's something like reverse endian or reverse bits or something like that, which should reverse it, at least in the circuit model. Yes.
Okay, great. Thank you. And that's all the questions we have as of now.
Cool. Great. Okay. We're making pretty good time. I'm used to doing this talk closer to an hour and a half instead of 2 hours. So I'll just now go through what if we want to actually run this on real hardware. So we can do that like really simply here. What we're going to do is we're going to import the IBM Quantum providers. And we're also going to use this package called least busy, because the real hardware, you have to kind of, your job kind of gets added to a queue if you want to run it on a real, because there's only there's only like a relatively small number of real quantum computers out there that you can run your experiments on, and lots of people want to run their stuff on there. So we will be trying to choose the one which is the least busy. Otherwise you do have to wait a bit more time to get something to run on real hardware. That's why we don't always tend to use it for teaching purposes, because then you have to sit around waiting for a while your result comes back. But essentially, if you want to do this yourself, the first thing that you'll need to do is you'll need to go to quantumcomputing.ibm.com. Actually, I can just show you this very quickly. We have time. So I'm already logged in, but if you're not, if you don't already have an account, you'll need to create an account. I think you can sign up with like your Gmail or your IBM ID, whatever you have. And you have this very nice kind of interface here. And you'll need to get this API token if you want to start using real hardware in your Jupyter notebooks. I already have mine set up, but if you don't have yours set up, you'll need to run ibmq.saveaccount and then your API token as a string in that function. I've already done this before, so you only need to do it once for your environment and then you're good to go. I've already done it. So for me, all I need to do is I need to assign a provider by just loading my account. Then what I'm going to do is I'm going to select a device. So what I'm going to do is just call the provider backends. I don't want it to be a simulator, so I'm setting simulator false. And I'm just looking for any device that is larger than 2 qubits, because we need 2 qubits at least to run this algorithm. There are a couple of like 1 qubit hardware devices out there, so we don't want to use those. So if I just run this, I can see, okay, it's selected for me IBM Q Lima from the Open Hub. So these are all, there is a selection of free free backends available. You can actually see them if you go into the IBM Quantum account. If you go to, can I remember how to do this? I don't do this very often. If you go to the services tab, you'll be able to see which systems are available to you. So some of these are ones, like if there's a lock, you basically you don't have access, but there are a few here that you know, are free to use for anyone in the public. So we can see there, like this is the, I think it was IBM Q Lima that the least busy function selected for me. So this is the spec for the hardware that has been selected. And I'm just gonna, I might have messed up some of my circuits now, but I'm just going to check that I have. Okay, we have our nice Deutsch-Jozsa circuit here. And so to run this on a real device, essentially I'm going to run that same execute function that you saw earlier. And this time, instead of the simulator, passing the simulator as the backend, I'm going to pass this least busy device that I've just called here. And so what you'll see is, you know, it's going to take quite a while, although actually that one took surprisingly not very much time. But sometimes if it's a busier day, it can take a little bit of a while to check, to get the results back. So you can run job.status to check on the status of your job. That one went through like super quickly. So it's already done by the time I run this job status, but sometimes it does take longer. So you can call job.wait for final state and then call the status. And then that will just kind of, yeah, it will output the information when it's done. So essentially what I've just done there is I've basically sent my circuit off to that a real quantum computer somewhere. I don't know where location wise that one's actually based, but it sent my circuit job there. It ran my circuit and then recorded my results. And so I can retrieve that result, get the counts, and then print it out the same way that I did previously, arrange it in a nice histogram. And we should see, there we go. We can see for sure that it was a balanced oracle. The reason that we've run it with multiple different shots is so that we can see that with the real hardware, we do get a few anomalies here of getting the wrong answer. And this is because when it comes to the real hardware, you get a lot of kind of errors present in the way that the system is set up. And so one of the easiest ways for a very simple circuit like this, the best way to kind of eliminate all those errors is to just run the experiment many times with multiple shots so that you can see just probabilistically which result is the correct one. The more the hardware is improved, the less errors you get, but there's also things you can do to your circuit to make it, to kind of optimize it a bit better for the hardware that it's being run on. And there are a lot of different ways that errors can creep in when you start using real hardware. And there's similarly lots of different things you can do to mitigate that. And it's a whole kind of, it's a really kind of vibrant area of research in how to make near-term quantum computers more usable by mitigating the errors that we see, because it will still probably be quite a while until we get perfect qubits that behave correctly every single time. Yeah, and then if you want more information specifically on the Deutsch-Jozsa algorithm, there is the Qiskit textbook, has a whole chapter dedicated to Deutsch-Jozsa. The Qiskit textbook, okay, I'm just like tooting my team's horn here a bit, but the whole of the Qiskit textbook is a really fantastic learning resource if you're just getting started with quantum computing. It explains all these concepts in more detail. It gives you examples of how to run things with Qiskit. You can see all of the maths that you want. Yeah, it's really good for getting a really in-depth look at all the different concepts that we've covered today, and much more. So yeah, I think that pretty much brings me to the end of the content I have prepared. If there are any more questions, I'm happy to answer them.
Yeah, to start off, I have a question, a logistic question about tokens. So like the website you provided, I'm wondering, like, will IBM be providing tokens to our participants? Maybe Brian's the more appropriate person.
Oh, so your tokens, anyone can get a token. It's so just by like logging into the platform, you're just by creating an account, you get a token associated with your account. Right. And it's a completely free platform, like anyone can sign up to use it. You can just log in with your Gmail, whatever. If you just go to quantum-computing.ibm.com, like you can do that right now and just log in, and then you'll get the same, how do I go back to my home? You should get, once you create your account, you should be shown the same kind of screen when you enter, and then your API token will show up here. There are a few of the providers that I just showed you here. So of all of these, like anything without a little lock sign next to it is basically a free hardware backend that is just available for the general public to start using quantum computers, get executing circuits on real backends, which is, it's a really nice thing that IBM does, is like making these services freely available for people to be able to use. Obviously, you're not going to be able to do very complicated things, because I think the biggest one they have freely available right now is only 5 qubits. If you want to start doing a lot more heavy duty research into this area, you might start needing more like, 10 or 20 qubits, then you'll have to go for like a paid tier. But yeah, for very simple problems that you're just, for learning purposes, like these are really good options.
Yeah, brilliant. That's really great to hear. Because I know some other platforms, they require like credits and not as simple as this is. Yes.
No, yeah, it's only if you want to start doing stuff with like a lot more qubits that you'll need to do that.
Mm-hmm. Yeah, we have another question in the chat that asks, how many shots are needed to run our program on real IBM Q in order to be accurate in the probability output? Yeah,
I mean, that's a difficult question to answer, because the more shots that you do, the more confidence you can have. So if you just won one shot on a real hardware, you're never going to be able to be certain that you're not going to be certain that you're getting the right answer from that. And then with just 2 shots, you'll have like slightly more, chance that you think it's correct. Like I wouldn't say there's any like minimum threshold for like you can be absolutely certain, but I think normally people will go for about 1,000 shots, at least for very small computations like this.
Awesome. Let's see. Just waiting for more questions to come in.
You can also see the simulators here. One other cool feature of this platform, while I have some time here, there's also the composer and the lab section. The composer gives you like a really nice kind of graphical user interface where you can do kind of like drag and drop, kind of make your own qubit kind of visualizations and things, which can be really nice for like playing around with how the circuits work. And you have different forms of, you can visualize the probabilities. This is a Q-sphere visualization. You also have here a lab section, which will open like a Jupyter lab in the cloud for you. It takes a little bit of time to spin up, but basically and Qiskit comes already like pre-installed in this environment, so you don't have to worry about setting up Qiskit locally or anything. So I can select which version of I want, and then already I have Qiskit used here. And again, it's just like a Jupyter notebook, but in your browser, and it's already got Qiskit installed and everything. So you can do the entire workshop that I just did in the Quantum Lab. Actually, maybe that's something that I should do in the future, because that would be quite cool. But yeah, for this time, I just did it on my own local machine.
Yeah, lovely. We have two more questions about the platform. Are there any limitations in the number of circuits that we can run in a given job list?
That I do not know. I think it depends, not that I'm aware of, but normally people would just probably do like one circuit per job, unless you were doing a more complicated algorithm with multiple circuits. I don't know. I think the limits on the number of circuits per job depends on the specifics of the provider. So you would need to have a look at the documentation for those specific providers for exact numbers. But yeah, I've never hit the limit. I'm sure there is one of like, I don't know, 800 circuits or something big. I think it also depends on like your depth of circuit as well, like how many gates you have. But yeah, you'd have to look it up separately.
Yeah, I imagine that's the same case for shots, right? There's going to be a max number, but you don't usually hit that.
Yeah, but like it's so high that normally you wouldn't really hit it.
Mm-hmm. Great. One participant wants to know if you have any advice on choosing the right simulator. Yeah,
so that really depends on what kind of output you want. So you can do state vector simulators if you want to get a state vector output. The simulator that we use was just the basic one, which was I think is a chasm simulator under the hood, which will give you like counts objects back. So yeah, I think you can actually also see in here, if you go to services, you can look at the simulators. Yeah, so you get state vector simulator, a chasm simulator, stabilizer simulator, extended stabilizer. So I don't even know what those do. The most like common ones I think are chasm and state vector, at least for like the type of things that we're doing. And yeah, like a state vector simulator will just return a state vector to you, and the chasm simulator will return like kind of counts objects. So it depends on the output that you want.
All right. On a related theme, what's the difference between emulator and simulator?
Are we speaking like generally, or like in this context of?
I'm thinking this context. Can the person clarify?
I'm not familiar with the concept of like a quantum computing emulator versus a simulator. I would assume like Qiskit pretty much just works with like uses those terms interchangeably. Mm-hmm. I know in like maybe the broader software engineering industry, like maybe they have more specific meanings for different contexts, but I think at least within the context of IBM Quantum, they're essentially the same thing.
Okay, yeah, I think that answers the question. Yeah, we have one more question. How to get a density matrix from a circuit where some operation depends on a measurement result on some other qubit, for example, in quantum teleportation?
Sorry.
That's a lot.
Repeat the question.
Yeah, actually, how to get a density matrix from a circuit where some operation depends on a measurement result on some other qubit. And I'll paste it in the chat too, if you prefer to read it.
Yeah, this was a question that came up in my head as well, because some algorithms rely on feeding forward the result of a classical measurement and then conditioning a quantum operation off of it. I was wondering yeah, maybe that's what this is asked, because that would create a kind of quasi, classical distribution that'd be represented by a density matrix.
Yeah, so there is work currently being done in Qiskit to allow things like C-ifs. So depending on the classical result of, like, say you do a measurement, and then depending on that classical result, you can then like do more operations like within the same circuit. I am not sure if any of that has been released yet. I know it's like a heavy area of development right now. So I couldn't confidently tell you how to do that. But I believe it is going to be like become more complete in one of the upcoming releases, or at least partially some of it might have gone out already in the most recent release. But I don't have like a nice fully created example to show you. But yeah, stay tuned. Keep an eye on the Qiskit documentation. Have a look at what's going on in the GitHub. There's probably some examples out there already, like that are kind of getting produced while things are still kind of, because things are kind of changing at a pretty rapid rate until like there's like a solid release out of those features. But yeah, coming soon.
Yeah, this came up when I was working on a quantum error correction project as well. That quantum control uses a lot of those. But maybe you could talk a little bit about the principle of deferred measurement and how you can get around this issue.
Sorry, what do you mean specifically about deferred measurement?
Oh, so like that if you're conditioning off the result of a classical operation or a classical bit value that you've found from a measurement from your circuit, that you can replace that with a fully quantum measurement and conditioning. And is that, I mean, maybe I'm misinterpreting the principle of deferred measurement.
Quite possibly not. It might just be quantum error correction is not my specific field, so it's not an area that I can speak confidently to. It's not an area of the code base that I'm most familiar with. But yeah, so I would maybe go and look at some more some of the more kind of like tutorials that focus on that area. That's not something that I can give you a nice example for right now.
Okay, awesome. Yeah, sorry to hit you with that.
No, that's all right. This is the thing with quantum computing. There's so many different fields and areas for it. My specialization is probably more towards like, I'd say like at the algorithmic level for like Qiskit applications, and like chemistry, for example, is my first love. So that means that like that's where I spend most of my time. But then other people maybe are like super passionate about quantum error correction. But if you ask me the first thing about quantum error correction, I'm like, I'll go look at James Wotton's talks. He's an awesome expert in that field. So it's really, that's one of the things that I like about this this technology, is that it's such an emerging field that people are developing stuff in so many different areas that, rest of us don't know necessarily much about what's happening in other spaces. There's like, whatever your interests are, you can probably find some little niche field of quantum computers that, quantum computing that is exploring that. I know some people are looking at like Raspberry Pi, running Qiskit on Raspberry Pis, for example. There's like quite an active community in that, which is such a random corner of the field. So yeah, apologies. Quantum error correction and deferred measurement is not my specialty. Do we have any other questions?
Yes. First of all, there's gratitude from the audience that asked the question about the density matrix. Thank you for answering that. For another question, for iterative algorithms such as gradient descent, how can we just combine the whole process in one job in this platform?
Yeah. So for iterative processes like gradient descent, yeah, again, it really depends on the specifics of the problem, and so you might reach a limit where like, and like how much time you have. So if you like package everything in one job, then sometimes and again, it depends which hardware you're running it on. If you're leveraging Qiskit runtime, which is another kind of new feature, which lets you run things kind of quicker. And if you're using certain, like, if you're simulating and you want to use like DAS clusters, you can like run the different jobs concurrently, and you can split your circuits into different jobs. So yeah, like the short answer is it depends. It depends on the size of your problem, how many circuits you have, how long it takes to run each circuit, how much, like which device you're using, and how much time it takes to get stuff back from it. So yeah, that's kind of something that you would need to explore depending on the specifics of your problem. So sometimes like it would not be efficient to just like run 1,000 circuits, I think, in one job. Sometimes you might want to like batch them in multiple jobs. But again, it really depends on the specifics.
Yeah, absolutely. And another question is, can we code with Qiskit tensor networks like MPS and TTN?
Qiskit, what, sorry?
Tensor networks.
I don't know what that is.
But I think this is like...
Is that like a TensorFlow plugin to Qiskit? What is this? Is this like a machine learning thing?
I think it has to do with machine learning. I'm not sure. Ben, do you have any idea?
I haven't heard of this either.
I'm not sure what you mean. Either it's like some area of the stack that I'm not super involved in, so I'm not aware that it exists, or maybe they got the name wrong or something. Maybe it's some third-party package that just uses Qiskit. Yeah, sorry.
Yeah, and with that, I think that's all the questions we have as of now. Oh, MPS stands for matrix product state.
Oh, I see what you're saying. Yeah, so I think there's a module called Qiskit Opflow, which lets you do more of those advanced and like the operator classes, which I think is possibly the direction that you're looking in for those more kind of mathematical, kind of structures. Yeah, I think, if I'm understanding that correctly. What I can show you all right now is I'm not sure if the background of your audience is much into the kind of like software side of things and open source, but oh no, that was not the link that I wanted this one. If you're in GitHub and you're interested in kind of, sometimes the best way to find information on what is available is just to dive straight into the source code itself. There are so many different repositories that we have available, from like the providers to the runtime. Qiskit-era is like the main repo, but there's also a lot of other things like Qiskit-era for those of you that are looking more into the oh, I'm so sorry, that was my doorbell. I gotta go check that quickly. I'll be back in like 2 seconds.
Yep. Yes, and everyone just hang on tight while we wait for Abby to come back.
Sorry, guys. It's the joys of working from home and extended 2 years of a pandemic. Yeah, so I was just showing you, this is our main kind of GitHub organization called Qiskit, where you can see all of everything that I've shown you today is pretty much all open source. So you can dive into the source code yourself. If you're interested in contributing to any of these packages, like you can definitely go ahead and do that. If you go into, for example, the main Qiskit-era repository, we have, you can see the entire code base here. You can have a look at, we have 600 open issues currently, and like a team of about 10 to 15 people working on it full time. So if anyone wants to kind of jump in or pick up any issues, you're very welcome to. If you filter for tags with good first issue, then you can see the slightly kind of easier issues to get started with. If you're new to open source, new to Qiskit, yeah, there's also like a range of different packages that are written in a range of different languages as well. So if you're maybe not the keenest Python developer, but you really like C++, you can go and contribute to Qiskit-era. If you are more into Rust, we have a package called RetWorkX, which is all built in Rust that you can use. And there's actually also some Rust stuff happening in Qiskit-era as well. There's also the Qiskit textbook as well, is all like, you know, there's a website that goes with that. So if you're a front-end developer as well, you're welcome to contribute there. Yeah, the community is very, is super welcoming, and we want to get more people involved in the quantum industry through code. So I definitely encourage everyone to go have a look there. And some of the more maybe like specific questions on like, what is this feature that I can do to like, how do I get this, how do I reverse the endian of my qubits or something, like you can find that information by looking through the code itself or the documentation as well. They're really massive code bases, so it's impossible to know everything off the top of your head, but that's why there's documentation and why it's all open source. You can go and look into it. Yeah, I just wanted to plug the open source side of things while we have some time.
Yeah, absolutely. This quarter at Stanford, our Stanford Quantum Club is leading a class called Open Source Projects on Quantum Computing. And that's basically what we're working on. We match students with people like you and work on open source projects. So it's really exciting. Yeah.
Nice, awesome. Well, if you start contributing to Qiskit-era specifically, like you'll probably see me hanging out in the GitHub and answering your questions on how to get your environment set up, how to run your tests. And yeah, we're a nice bunch.
Yeah, for sure. And with that, since every question has answered, I'll wait for 10 seconds. For any last minute questions?
Yes, a quick question from a participant a while back. So they're wondering, for the hackathon this weekend, are the workshops from today sufficient preparation, and what other resources would you recommend that they refer to if they want to prepare for the hackathon this weekend?
So I'm not familiar with the details of the hackathon itself, but in terms of extra resources, definitely go and check out the Qiskit documentation. So that's qiskit.org/documentation. So for like specific details on, this is all the API references. So all the details on like how to apply this gate or how to do this, you know, tensor product matrices calculations. Anytime you need to look up like a specific syntax for Qiskit, it's impossible to keep it all in your head, so refer to the documentation if you can. I'd say for more in-depth information on the algorithms themselves, also the Qiskit textbook is a really good resource, which I think I had up here. Yeah, it's qiskit.org/textbook, which has a lot of chapters on like more diving into the theory behind the algorithms, as well as how to implement them in Qiskit as well. Yeah, but I don't know the specific detail of the content of your hackathon.
Yeah, no, that's great. And for that question, if you can always join our Discord channel and ask relevant questions in each of the different challenges, and I'm sure there are people who will be able to answer you. Yeah. And with that, I wanted to say thank you, Abby, for a great presentation. It's from me, but also from the audience. They agree. Thank you so much for taking the time today to speak to us. For any viewers, once again, with further questions, please post them in the IBM channel on the Discord. And the recording will be made available later on Twitch at the exact same link. Just scroll down to the video section.
And just a quick plug about the next event today. There will be a social mixer from 9 to 10 Eastern. I understand a lot of viewers can't make that time zone since it's late wherever you are. So don't fret, and there will be more social events scattered throughout the next few days as well at different times throughout the day. Yeah, so thank you so much. And
yeah. And if I can plug that quickly, that's going to be a quantum game night. So get on Zoom to play a ton of games in breakout rooms, meet friends. It's going to be fun.
Perfect. Hope to see you all soon.
Thanks, everyone.
Yeah, thank you so much.